Thank you for joining me today for this presentation on the composite water swollen spiral wound membrane module for raw biogas purification. Biogas is a promising renewable energy source, but its impurities, such as water vapor, carbon dioxide, and hydrogen sulfide, make it unsuitable for many applications. That's where membrane technology comes in. It can effectively remove these impurities and turn raw biogas into a high-quality fuel. In this presentation, we will discuss the composite water swollen spiral wound membrane module, its design, operation, and performance, and how it can be used for raw biogas purification. So, let's get started.
The authors of this collaborative research work are Albert S. Kim as a speaker from University of Hawaii at Manoa, Department of Civil and Environmental Engineering, USA. The team members from the Institute of Environmental Technology, Technical University of Ostrava in Czech Republic are Petra Wojnarova, Panagiotis Basina, and Jiri Ruzin. Dr. Pavel Izek is from Czech Academy of Sciences, Institute of Chemical Process Fundamental. I am delighted to announce that we are embarking on an exciting international research collaboration between the University of Hawaii in the United States and esteemed institutions in the Czech Republic. By pooling our resources, expertise, and knowledge, we have the potential to make significant breakthroughs in our research areas and advance our understanding of critical issues in our fields. I am thrilled to be part of this collaboration and look forward to the promising outcomes that will undoubtedly emerge from our joint efforts.
Welcome to this presentation on biogas purification. Biogas is a renewable energy source that has the potential to play a significant role in reducing greenhouse gas emissions and meeting global energy demands. However, biogas contains impurities such as water vapor, carbon dioxide, and hydrogen sulfide, which must be removed before it can be used as a fuel. In this presentation, we will explore the various methods of biogas purification, including physical, chemical, and biological processes. We will also discuss the benefits and challenges associated with each method and highlight some of the latest advancements in biogas purification technology. So, let's dive in and learn more about biogas purification.
Biogas is produced during anaerobic digestion. The composition of raw biogas depends primarily on the input materials used. The typical composition of biogas ranges from 50–70 vol% methane, 30–50 vol% carbon dioxide, and other minor components such as hydrogen sulfide, hydrogen, nitrogen, ammonia, siloxanes, and water. By removing the unwanted components from methane, we obtain biomethane. Biomethane with a purity of at least 95% methane can be injected into the natural gas grid or used as vehicle fuel.
Currently, several technologies are used for separating methane from biogas, including membrane separation. Other processes include, but are not limited to, water or amine scrubbing, physical and chemical adsorption, pressure swing adsorption, cryogenic separation, methane hydrate formation, biological upgrading, and in situ upgrading.
All experiments were conducted using the industrial-grade spiral wound membrane filter DuPont Dow FilmTech XLE 2121, which is commonly employed for the desalination of brackish water. We decided to test this thin film composite membrane for biogas purification, and this developed method was also patented by one of the research team members.
The TFC membrane of the spiral wound module is in contact with the saturated water vapor of the feed stream. Due to the low temperature of the membrane, the water vapor from the feed stream condenses on the surface of the hydrophilic polyamide top layer and forms a water layer throughout the entire membrane surface. The top polyamide layer, when it comes in contact with the water, becomes swollen, and together with the formation of the thin film of water on its top, enables the gas separation. The separation principle applied on the membrane layer relies on the varying solubility of gases in water. By introducing some artificially added moisture along with the inherent moisture of biogas, a slender water film forms on the membrane's surface. Methane, being almost entirely insoluble in water, stays in front of the water layer and exits the filtration module as retentate. Conversely, highly soluble gases like carbon dioxide and hydrogen sulfide permeate through the membrane and constitute the permeate stream.
The main advantage of this separation method is primarily water saving compared to the water scrubbing technology. We primarily utilize the natural moisture of biogas, which is further supported by additional humidification. Therefore, the natural moisture of biogas is desirable for us, and unlike other technologies, we do not need to include a gas drying step before separation. Based on the experiments conducted so far, it seems that the lifespan and durability of the filters will also be high. No less significant advantage is that hydrogen sulfate leaves carbon dioxide in the permeate stream. Therefore, it is not necessary to have a pre-treatment step for incoming biogas by desulfurization. On the other hand, if we wanted to further utilize the waste permeate stream with CO2 and H2S, it would be necessary to address the removal of H2S.
In this research, a water-swollen spiral wound membrane module was used to separate CH4 from two feed streams, a synthetic binary mixture of CO2 and CH4 and raw agro-biogas. The laboratory apparatus was made from stainless steel tubes closed by clamp caps. The apparatus consisted of the main chamber for the filter and reservoirs for the water. Raw biogas is fed into the lower part of a stainless steel pipe, which consists of a chamber filled with water at a temperature of approximately 90 degrees Celsius. It then enters the filtration module. The TFC membrane of the spiral wound module was in contact with the saturated water vapor of the feed stream. Then, the water vapor from the feed stream condensed on the surface of the top membrane layer and formed a water layer throughout the entire membrane surface. After separation, the permeate stream with CO2, H2S, and H2 exits through the center of the filtration module. The resulting product is a retentate stream containing more than 95% methane.
In this picture, you can see the results of the separation of a synthetically prepared mixture of 52% CH4 and 48% CO2 with the use of one filtration module. The input pressure of the gas mixture was 3 bars. The inlet flow rate increased slightly from 1.695 to 2.068 liters, min1 during the 2 hours of operation. The flow rate of the retentate stream was almost constant, slightly fluctuating between 0.460 and 0.520 liters, min1. The retentate stream contained more than 95% of CH4, indicating the high-quality biomethane produced after 30 minutes of separation. A continuous improvement of the retentate composition was observed over time, attaining a maximum methane partial pressure of 98.4 vol% at the end of the 120 minutes. Maximum recovery efficiency was 49.9%.
In this slide are presented the results of the separation with the use of 2 parallel filters. Input gas for the separation had the same composition as the previous, the binary synthetic mixture of 52% CH4 and 48% CO2. The input pressure of the gas mixture was also 3 bars. The methane content in the retentate increased from 90.5 vol% to 94.3 vol% during the first 90 minutes and to 95.8 vol% for the next 110 minutes. Although the CO2 content seems to follow a smooth trend line, it clearly shows a sharper decrease before 90 minutes, followed by a short plateau for about 30 minutes, and then a gradual decrease. The maximum recovery ratio was maintained at around 58%. The average methane recovery efficiency, estimated as 56.7%, was 8.5% higher than that of the single filter case.
We also repeated the single module experiment for 120 minutes using agro-industrial biogas containing H2 and H2S and CH4 and CO2. The pressure was kept at 3 bar. The inlet flow stopped increasing after the first 30 minutes and remained almost constant. Although the system stabilized after 30 minutes, the partial pressure of methane was higher than 95 vol% after merely 20 minutes of separation. The system seemed to reach high efficiency soon after the filtration started. The recovery ratio was 49% and remained at similar levels to that obtained from the single filter experiments processing the binary mixture of CH4 and CO2. Interestingly, the presence of gaseous impurities contained in raw biogas seemed to accelerate the attainment of a steady state without significantly influencing the methane recovery ratio. The methane recovery ratio of the water-swollen membrane was less sensitive to impurity concentrations than to module configurations and operational conditions. It is worth further investigating the effects of chemical interactions between biogas molecules and their dissolution tendencies to recovery ratios, as well as other performance indices. However, the current experimental evidence shows the industrial potential of the water-swollen membranes to improve biogas separation. In our experiments, the raw biogas had an H2S concentration of 55 ppmv, much lower than conventional agro-biogas. In the retentate stream, the H2S concentration decreased from its initial value of 15 ppmv and reached 5 ppmv after 120 minutes. The decreasing trend indicated that the retentate concentration of H2S would be below 10 ppmv.
Here are our conclusions. First, the membrane module, initially developed for desalinating brackish water and consisting of a spiral wound composite membrane that swells when in contact with water, was employed to purify untreated biogas produced from biomass digestion. Second, to separate impurities from biogas, the membrane was entirely submerged in water, and a vacuum was applied to the side, allowing permeation. The results demonstrated the effectiveness of this separation technique for biogas purification. Third, at most operational conditions, the biomethane outlet stream achieved a methane proportion of approximately 98 vol%, and exhibited high purity levels. However, additional research is needed to reduce methane losses, despite achieving a 50% recovery efficiency.
We are very delighted to initiate and conduct the international collaboration between the University of Hawaii at Manoa in the United States and the Technical University of Ostrava and the Czech Academy of Science in the Czech Republic. If you have any questions or comments, please feel very free to contact us with the email address shown here.